as you're noticing now at the talks, both Sergey's talk, then Fish's talk, and now this one, we're talking more about meta research. Some of Fish's stuff was, some of Sergey's. What do we have to do to make sure our research is valid? What do we have to do to make sure the research can propagate and move forward? And some of that is looking at the research methods themselves, looking at the data, the tool sets, the suites, not just the individual algorithms. And so we were putting together a data set ourselves at my lab. I had a staff member saying, I want you to put together very large data sets on our server that the students can run their tools on, and so that they can validate their tools. And I want you to set this all up to reduce the work on those grad students. And she was starting to run experiments on people's tools to generate the ground truth, and we were noticing discrepancies. So we started thinking about this and looking at this. This led to this paper. Unfortunately, she couldn't make it here today, so I'll be talking about what this work was. The effectiveness of our binary analysis tools and techniques are often measured with respect to how well they map to something, the ground truth, the reality. But not all ground truths are created equal, we found. Not all realities are the same. So we want to challenge the community to come up with a standardized format for these things, the real answers, the real ground truth that everybody can share. This is similar to things other people have talked about. So again, we don't have the grad students or faculty spending all their time trying to reevaluate and rebuild things. This especially becomes important when we lead to things like machine learning. Machine learning is trained based on a ground truth. Well, if your ground truth is wrong, your machine learning model is very wrong. Accurately wrong. Consistently wrong, but still wrong. You know, garbage in, garbage out. Though one of my students says, no, what we want is garbage in, rainbows out. But I can't do that. At the same time, the definition of ground truth is context dependent, or maybe, as Fish was saying, application dependent. Because what are we going to use it for? You know, what are we examining? Are we looking to the correct decoding of instructions and data, basically disassembly? Are we talking about mapping the binary to complex structures such as functions and data structures and basically doing decompilation? The context matters when we're evaluating the effectiveness of the binary. It also matters when I'm examining normal code, obfuscated code, or malware, because those are different target environments that have different types of ground truth. Our work mostly looks at normal binaries. We're not dealing obfuscated, we're not dealing with malware. We're talking about helping the developers build secure code when part of what they're importing into their toolkit is something that hasn't been completely analyzed, or they don't even have the source code because it's legacy code, or it's a third-party library. So what I want to talk about first in this talk is a couple of categories of things we have ground truth with. And then I'm going to go back and give some examples to just point out things that we've seen that are kind of interesting. So first, where do we obtain the ground truth about which bytes are instructions? How do we know? Do we need to instrument a compiler to tell us this? Or is there sufficient details in the debug data, the dwarf data? Where do we get this? Why am I asking this? Because I've seen lots of papers say, well, and we map to the ground truth and we have a 90% accuracy, or accuracy is the wrong word to use, but let's say, you know, F1 values or our precision and recall. But I oftentimes in those papers, I don't see people say how they got that ground truth. Or they say, well, we got it from the debug data. Well, I looked at the debug data. It's not in there, so where did you get it? Or the debug data was wrong. We'll come back to that in a second. What about instructions? So I'm trying to say, did I get the right things as instructions? I tell you they're instruction. What if instruction is used as data? Right? Now, there are programs that run checksums on their own code. I've seen this for fault-tolerant code. So it actually has a pointer to where the instruction is and runs through it and performs a computation. A tool might say, well, that's data because it's being used in a computation. Or is it an instruction? I'll call that an instruction. But for just-in-time compiled code, maybe you'll have a bank, a data set of snippets of code that you're going to actually use, compile, and send off into the heap. But where it lives, it's data. Where it's generated, it now becomes code. So where it's lived is a code. so these are things we have to think about. What's real, what's not? Yeah, I'll leave it at that. So we recommend defining instructions as executable code as compiled into the binary. Instructions that are only meant to be copied and therefore only used as data should be categorized based on their location and not considered code. Well, no, let me rephrase that. But if they live in the data section, they're not considered code. If they live in the executable, the code section, we consider them code. How about functions? Now, I'm going to spend a bit more time on functions. Why? Because I've done a lot in terms of function analysis lately. It started when we were doing the DARPA Cyber Grand Challenge work because we were trying to add stack canaries and other features at function entry, function X, control flow integrity stuff. But we've been doing a lot of work on function boundary detection because our tools weren't precise enough, weren't correct enough. And so when I'm looking at functions, the first thing I have to ask is there a need to map the binary directly to source code, to the original source code? And if there is, what happens if a function is inlined? I took a function in the source code, but there is no corresponding true function in the binary. It's part of another function. So is that a separate function or is it not? What happens if the computer creates multiple entry points for a function? Which one's the start of the function? What if it takes the function, the source function, and divides it into separate compilation units, separate executables with separate entry points in the binary? In the binary, you can see it as 4 or 5 functions. In the source, it's 1. So which is it? What's the ground truth? If you're saying, I'm decompiling this binary into source, I'm using binary differencing, and I'm trying to say, hey, in this compiler, this source function mapped to here, and this compiler, this source function mapped to here, 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 and here. That's a one-to-one, not a one-to-one correspondence, but I need it. So what are we looking at? We got to think about this, because compilers do weird things, as was mentioned earlier today. So do we define a function with strict adherence to the source code? And how about functions with tail calls? That was mentioned. The last instruction of the function is a call. They'll optimize it away by turning it into a clean up the stack, make it a jump, so your return now doesn't have to do multiple returns. I was looking at one tool, what was it? I won't name the tool, I don't remember which one it was. But they considered jumps as just part of the same function. They allowed functions to be discontinuous within memory. And so suddenly they had a whole lot of different chunks of code with all this tail calls, part of one function. Because it wasn't a return. It wasn't a call. It was a jump. So it had to be part of the same function. Is it? If the compiler optimizes away the tail call, am I jumping to a function or disjoint part of the code? What about a compiler that allows a function to fall through to the next function? Oh, the next function you're calling is just right here, so we won't do a call. We'll just clean up the stack and let it just execute it. Are they part of the same function, or is this 2 different functions? How do we know? What if a function's not called? You loaded a static library, but it's part of the library that's not used. It's not reachable. It's unreachable code. Is it still a function? What about the functions that are added by the compiler? The startup and shutdown, the initialization, finalization functions that you see in the binary. Are they functions or not? I've seen some people say, we're doing function boundary analysis. We ignore those because they're not part of the source code, and we only want to analyze and find the things that came from the source code. And again, can functions have more than one entry point? I'll show you some examples of that. So when we think about this, we say, oh, one others. Besides function entry points that start a function, how else do you define a function boundary? Look at its end. Do we assume all the bytes are contiguous? Or functions can exist different places in memory, discontinuous? Where do we get the data that says where the function ends? Oh, I got it from the symbol table. Whose symbol table? Which compiler? GCC, CLang, or Clang? I like to call it Clang. GCC, Clang, or ICC, the Intel compiler? Intel compiler includes padding bytes as part of the last bytes of the function. GCC and Clang don't in the symbol table. Wait, those are different. Who cares? Which one are you using when your tools are there? I was looking at one tool that was done years ago. doing function boundary analysis, and they had a function that calculated were they correct. Well, they made this available. Yes, we downloaded, we looked at their tool. It says, am I correct? Are the function starts the same? That's a correct answer. Is the function end I reported correct compared to the symbol table or earlier? And I made my function too short. If it was too short, they counted it as a win, that it was correct. Why? That was a hack because of the Intel compiler putting padding bytes in there. What if the last byte of the function is not executed because the compiler didn't know it was calling a terminal function, a non-returning function, so the next instruction would never ever be executed? Is that still part of the function? These are all questions we have to, and I've seen different things with different papers, so which one's right? My tool counts the padding bytes, because I figured out it was running the Intel compiler, and the Intel compiler said it's padding bytes, so I count them. And then I used my same counting metric that said, oh, if you don't exactly match what the binary says in the symbol table, you're wrong. And so I was able to beat all the people who didn't count the padding bytes. We win. I love winning, and then you publish the paper because it's 100% correct, right? So I recommend defining functions as logical units within the binary that have an entry point and one or more exit points, and the collection of executable instructions in between, including exception handlers. Oh, that's a whole other thing. If you do the control flow graph of a piece of code, there's no control flow in there to the exception handler that's tied to that piece of code. Most compilers will attach that exception handler right after and count it as part of that function. Oops, that was another thing I didn't mention, so we have to deal with that. Exit may be called to non-returning function, a jump to the start of another function, or a return. And I'd say all that maps as close as we can to the source code. But it's a single function. It's contiguous. I don't count inline functions as functions because the compiler is treating them as a macro. So if it's treating them as macro, I'll treat it as a macro. I don't count compiler inserted. I do count compiler inserted functions as functions. Why? Because they exist as part of the binary. And some attackers actually use them. There's been attacks using the standard built-in libraries or built-in functions for their attacks, so we may as well count them, we may as well analyze them. If it exists in the code and it can be executed, it should count. What about pointers? Other references, indirect jumps, calls. Within the code, these exist. Within the data section, there will be, or any data section, there will be pointers or references to code and to data. And within code, there's pointers or references to code and data. They may be absolute values. They may be relative values. Personally, I don't think there's too many questions related to these values as they are what they are. But people sometimes in their analysis have to figure out that's what this is. We have jump tables. So you have an indirect jump, usually used for switch statements. We have function pointers and other values that are used for this. The location of these values all fit into the categories, pointers or references to code, and I just want, we've got to think about those. Where do we attain the ground truth about which bytes are these references and pointers, especially in the data section? I've got a collection, 32-bit binary, I've got a collection of 4 bytes, contiguous bytes. Are they a pointer or not? Are they being used as a pointer or not? How do I know? Who tells me that? Jump tables. They're generated by the compiler for the switch statement. You have a table of all these addresses. How do you know? How do you know where that table starts around? Who tells you that? When we did the Cyber Grand Challenge, we actually searched the code for contiguous 4 bytes that reference something in memory, and we said, that's got to be a code pointer. Or if it points something in the data section, it's got to be a data section. We just guessed. We weren't always right. It was a hack, a heuristic hack. Some people say use your relocation data for the pointers. But if your program, if it's fully linked binary, it may not have the relocation data, especially if it's a position-independent code. So if it doesn't exist, you can't use it. So our recommendation, values are what they are. We don't think instrumenting a compiler to find these values is going to be the best long-term solution. We've seen people do that. But then you've got to re-instrument every compiler that comes along that you want to use. We've got to find some other way to get the data without re-instrumenting compilers. If the debug data contains all typing information, maybe we can extract it from there. That means your compiler has to generate debug data. I was doing some tests on a compiler that could not generate dwarf data. Well, if it doesn't generate it, I don't have it, I can't use it. There are special functions. The non-returning functions, for example, that we talked about earlier. Where do we get the ground truth about these? And I don't mean just about exit and abort. I mean Jim's exit, the function I wrote that happens to print an error message first and then calls Jim's second attempt to exit, and then that calls an exit function. I have to recursively go back. I have to do a control flow analysis and figure out, is everything I'm calling here possibly a terminal? And then check each of those and work my way down until I find out, yep, the call tree, everything ends in a terminal, then it's terminal. I have seen tools that embed a list of non-returning standard library functions. We have to keep that list up to date. I think we found 8 in libc that are non-returning. How does it affect your control flow? You know, is an instruction after a call to a non-returning function part of the same function or not? Everything else, your whole control flow gets to there. That's the last instruction. Nothing else could possibly go past there. You call a non-returning. There's another instruction. Is that part of that same function? What do you think?
I tell you what anger does.
What does anger do?
Anger doesn't consider it part of the function unless someone else executes it.
Okay, anger doesn't consider it. I actually was doing work with a company that did real-time operating system. They deliberately put code in calls to non-returning function in case the non-returning function accidentally returned, because they had seen this in a real-time system. And usually what it was another error that grabbed that return address from that call from the stack. And because I saw him, I said, why are you doing this? You're calling exit or abort. Why do you have another instruction there? He says, because sometimes I call abort, but that instruction still gets executed, so I want to make sure we're safe. And he'd seen it in real code. Well, that's interesting. So non-returning functions are special, need to be recognized, need to be documented somehow. Operating system calls may need to be documented with the non-returning feature. I hadn't thought about error being possibly non-returning, but with a certain constant value in there, it is non-returning. We ignore that in our tool, but I'm going to look at that one now. Everything else I think we should be able to be recursively analyzable, but you got to be careful again, where do you get the data? Also, any functions inserted by the compiler, again, they're part of the program, need to be treated as part of the program. Here's some examples. This is from a binutils ICC compiler. That was the older Intel compiler. They now have ICX, which is now LLVM based, which is different, but this was a couple years ago. These are listed as 2 different functions in the symbol table. The first one, this is AT&T syntax. So the first one takes things from the stack that were passed by the stack and pushes them into registers, then falls to the rest of the function that assumes everything was called using a register passing mechanism, even though it's 32-bit. 32-bit calling convention normally is pass on the stack. Intel decided we're going to optimize, and we're going to pass everything on registers. We're going to leave a placeholder stub in place for anybody who happens to call this function. If we export it as part of a library, somebody else calls it, they will call it on the stack. But if internally we call it, we call the one that assumed everything's passed in the registers. And so if inside this program, the linker.c or whatever, when all that was compiled together and put into whatever binary was there, no calls were made to this first line. No calls were up here on the fixsims, just fixsims dot were the calls. This falls through. My tool cries when it sees this. It says, okay, what am I generating? I see this as one function. Oh wait, but these are calls to here. This fell through. Oh, we got to hack it. We got to optimize it. But what's the ground truth here? What's the reality? Is this one function or 2? The symbol table says 2. My gut tells me 1. One of my students said, let's call it 1.5. Here's one. I'm going to give a couple slides on this one. Notice this is from the symbol table. There's another using ASNew compiled with ICC. Notice integer constant, not just dot, but dot, dot, 0, dot, dot, 2, dot, dot, 3, dot, dot, 4, and dot, dot, 1. Expression dot, dot, 0, dot, dot, 1, and there's operand and operand dot, dot, 0. I see 5 different integer constant functions here in the symbol table, because the optimizer compiler optimized them. And actually, if we look at this, here's two of them. What it realized was that the first argument, every function or every call in that program that was compiled and called these, passed a constant into this argument, the radix argument. I don't even remember if it's the first argument or not. Because this was for translating a text string into an integer. A text string of an integer constant into an integer, and it either could be base 2, base 8, base 16, base 10. What was the other one? So there's 5 of them it chose. So base 2 is down here, base 16 is up here. Same line of code, compiled different ways because it can optimize it. Oh, I know this is radix 16. I'm going to do some shifting here. This is just radix 2. I'm going to just do an addition and a less shifting. The optimizing compiler figured it all out, went through the code. Also, there's part of the code, this number equals number times radix plus digit that they used. Part of the code of the interpretation that was in a switch statement. The switch said, oh, case 16, we'll lose that part in the integer constant ... 2 one. If it was case 2, we'll include it here, and then the part that was after both include. So subdivide the function, broke it up. How many functions do we have in this code then? 1 or 5? If I'm decompiling, I'm going to decompile it into 5 functions. In the executable, there are 5 functions, 5 separate places things could be called. Oh, and if I was doing binary differencing or similarity analysis, well, the other compilers don't do that, just Intel. So if I compile it with GCC, I see 1 function, Intel, I see 5, I get a 5-to-1 mapping. Here's another one we had. So down here, there's just a simple while statement. So we have a jump here at the beginning of the while, a jump at the end of the while to loop it. IDAPRO says, you're jumping past all these no-ops. That's a tail call. And IDAPRO, when it does its function boundary analysis, says, these are 2 separate functions. Oops. This is the end of one, this is the other. And I have no idea what it thinks this is. And I have no idea what this is. It's never executed. So I don't know where that line came from. I haven't figured that one out yet. Or here's another one. We have a jump pointer, indirect jump, used for optimize a switch statement. IDAPRO cannot determine what value is in this indirect because it just did a bunch of different things. So it said, that's the end of my function analysis. Function boundary's done. I've seen people write papers say, I grab my function boundary information when I do reverse, had IDAPRO do my disassembly or Geiger do my disassembly, but they're not 100% correct. So if you're training based on IDAPRO data, you'll match what IDAPRO says, but it doesn't mean you're right. And if I map it with somebody else, I'm wrong. With dwarf data, I've seen several papers state they use debug data for ground truth. That's all they say. I use debug data for ground truth. Great. I use the Bible for ground truth. Okay, what's that mean? When looking at dwarf debug data, there's some issues. One I found that we ran into, one of my students misinterpreted something. The high PC value, so there's a tag and it says in the DIE data, it says, oh, this is high PC. Oh, that sounds like high program counter, right? So it'll be an address. Well, there's a flag associated with it to tell you if it's a hard-coded absolute address or a relative address. And if you didn't notice that was also in there, you got the wrong address. But it was said high PC, so it should have been right. But it was just relative. So those are small things, but people who write tools who didn't check that, their tools would be wrong and they wouldn't know. And the community almost never sees the tools that generate the ground truth that then you're validating your stuff against. Not all compilers even have complete information in the dwarf data. The dwarf data for that, where was it? This integer constant data only mapped to integer constant 0. It didn't map to the others. So the dwarf data wasn't complete in this. Intel didn't fix it and do whatever it needed to do, so I didn't know what to do with it. So, oh, we've got the dwarf data. We'll use it from there. Did you check that your data is correct? I'm validating things, and this is correct. The example I give my students is, I currently have in my bathroom 2 scales for weighing. I don't know why we kept the second one, because we bought the new one. The second one's still in the bathroom. The second one weighs me 4 pounds lighter than the new one. Or the first one weighs me 4 pounds lighter than the new one. I like that. So I'm validating. I buy a third scale. I get on that. This tells this weight. I get on the old one. Well, the old one says 4 pounds lighter. The new one must be wrong. Well, it says, no, the old one's wrong. Well, how do I know that? That's the data you generated. You never checked. Because getting ground truth is not the exciting, sexy thing. It's not going to get you a publication. So we'll just check it and publish it, and we'll say, we're fine. Everybody knows what we're talking about. No, I don't. Because when I do it, I see different answers. So I don't know what you're talking about. There are a couple tools that generate ground truth by hacking the compiler. Great. Pang et al., these are cited in the paper. They revised the compiler to admit all of the ground truth information they needed for their study. Lee et al. Used the intermediate representation that was generated in the compiler, such as generated assembly code listings, to assist in their generation ground truth. But they only work if your compilers, for the compilers they're generated for. So I did tests with GCC and Clang and Intel ICC and ICX and one or two others we were starting to play with. And they're not all instrumented, so I can't, and the ground truth is going to be different between them. Why? Because they have different addresses. So even if I did function boundaries, I wouldn't know what the right addresses are. And like I said, Intel broke one function into 5. What's the ground truth? And newer versions of compiler. So there is a toolkit out there. I think it's called KIT, K-I-T. It's on GitHub. They went back and have 7 versions of Clang and 7 versions of GCC that they've compiled all these things with across this whole data set, and they compiled it for Linux, or for Intel and for ARM, 3264-bit. They use the LTO option, and you're right, I've used 01, 02, 03, 04, fast, speed. I don't use LTO. LTO breaks my tools, link time optimization, because actually it breaks OBJ dumps disassembly of some standard functions because they're compressed together in a way, and OBJ dumps disassembly fails. And so my tool fails on 13 test cases because of that. Knowing the ground truth is essential when evaluating the effectiveness of binary analysis tools. We've seen a few instances where the ground truth was incomplete, misleading, misinterpreted, or even hacked to get results the authors wanted. Oh, no, I should say, I wouldn't say the authors were deliberately misleading the community. They didn't focus on the importance of having the right ground truth or talking about it in their paper. So without the existence of well-vetted tools and or data sets with ground truth, we're going to struggle. We're going to struggle with the ability to accurately build, evaluate, and gauge other tools comparing with each other. If we use incorrect ground truth when doing machine learning will completely map and model that incorrect ground truth. So I recommend a discussion among the community for these things. Let's figure it out. Let's try and do it. I don't believe custom tools will be the best. If we can use Dwarf Debug, compiler-generated simple tables, those are a good start. I still think it would be useful to have a fully vetted library of binaries complete with source code, a whole test suite we can do, full debug data, database containing all the ground truth data we're interested in for a wide variety of microprocessor architectures, operating systems, compilers, programming languages. That's what I want to see. And yes, I don't want my grad students building it from scratch every single time. Or what's worse, I have somebody working on a former master student's project. Students shared all the code with me, but none of the data set, which they had converted into a special format. So now we have none of the ground truth they used to generate their stuff, and we're lost. It's making it harder to use the tool. So, we want to do that. That was my fault, but. So anyway, that's my soapbox here. Any questions?